Hi, we're going to talk about two capacitor circuits now. This is the circuit that we drew in class. Notice here there's two capacitors and there's two resistors. So just to get started, I've written out the basic equations that govern this. So we have the equation that basically understands the voltage on this capacitor and its relation to this current, and then so on. So we have these four equations. Now let's count the unknowns. What are the unknowns inside this circuit? We have V1, V2, I1, and I2. So far, so good, but we also have these derivatives. So we have d by dt V1, and we also have d by dt V2. So there are 6 unknowns, and there are 4 equations. So in this case, we're not going to be able to, just given everything here, be able to solve this. However, what we can do is reduce this to 2 equations. So if we go through and sort of combine terms together and reduce it to 2 equations, what do we get? This is a good exercise for you to do on your own. This is classic 16A type material to be able to go through and grind this out. So we can basically collect terms and write out what do we know about d by dt of V1. So d by dt of V1, we know, equals 1 over C1 times V in over R1 minus V1 over R1 minus V1 over R2 plus V2 over R2. So notice what I've done here is I've basically taken these equations and I've written it out, combining them. So here I'm using the equation that this one here, and I'm using this together. So if we do this, then we can simplify this out. This is just equal to minus 1 over R1 C1 plus 1 over R2 C1. So remember, everything here is involving C1 times V1 plus 1 over R2 C1 V2 plus V in divided by R1 C1. So this is an equation that connects the derivative of the voltage on capacitor 1 to the voltage on capacitor 1, the voltage on capacitor 2, and the input voltage. Makes sense. Similarly, and I won't go through the derivation this time, we can do it for V2, and this is in fact a much simpler one. So again, just writing it next to this one, we have V1 times 1 over R2 C2. Remember, this derivative is coming from this equation, so it's going to be 1 over C2 in front of everything, minus 1 over R2 C2 V2. Now, notice there's no connection to V in here. So we have this system of differential equations. Now, to help us proceed forward and to have nice numbers, I'm going to write out make a few assignments of values to these resistances and capacitances. So for convenience, I'm going to say C1 equals C2 equals 1 microfarad. I'm going to pick R2 equals 1/2 mega ohm, and R1 is 1/3 mega ohm. Why did I pick these? I picked these so that these numbers would become nice. So using these, we get d by dt, and we can write this out into vector matrix notation. V1, V2 equals the matrix minus 5, 2, 2, minus 2 times V1, V2. That's this part here, plus 3, 0, V in. So we get this differential equation written out in matrix form. So again, to make everything concrete, let's assume we want to calculate the response to a transient here. We want to understand what happens if Vn started at some value and then changed. So suppose Vn equaled 1 volt for a long time. and then switched to Vn equals 0. So this allows us to understand the initial condition. So if the first voltage here, Vn, was at 1 volt for a very long time, you know that there's going to be no current through these capacitors. This Vout is connected to nothing, so there's no current here, no current here, no current here, no current here, which means no current here, no current here, which means all these voltages are the same. And so the initial condition, Vn of 0 equals V2 of 0 equals 1 volt. So we want to understand, how does this behave? So at this point, we find ourselves in a situation where we are essentially nearly stuck. We don't know how to solve differential equations like this, systems of differential equations. And unlike the case of a simple scalar differential equation, where we know what the answer is going to be, we basically can't even guess. We don't know what to guess here. So what can we do? Essentially, at this point, we only have a hope that we could perhaps change variables to some new variables that will somehow make this easier. However, looking at this equation, we have no idea what variables to change to. So to show you how basically trying something won't necessarily work, let's try something that'll turn out not to work. But it's useful to do it just to help practice, what does it mean to change variables. So let's try. This is blindly. Let's try the following change of variables. Suppose I define new variables. Instead of these, I use u's. u1 equals v1 plus v2, and u2 equals v1 minus v2. Maybe you think that the difference of these two voltages is something interesting, and maybe the sum of these voltages is something interesting. So you give it a shot. If you take this, now you need to use these changed variables and see what a new differential equation is in terms of u1 and u2. So you can just start, you just differentiate this. d by dt u1 equals, well, take the derivative of both sides, d by dt v1 plus d by dt v2. But we have expressions for this up here, so we can substitute these in. And if we substitute these in, we get minus 5 v1 plus 2 v2, that's from up here. And then for v2, plus 2 v1 minus 2 v2. Okay, so we're getting some kind of cancellation. This equals minus 3 v1. But we want everything in terms of u1 and u2, so we can kind of make little notes for ourselves. What are v1 in terms of u1, u2? So v1 equals clearly u1 plus u2 divided by 2, and v2 clearly equals u1 minus u2 divided by 2. So we substitute this in, and we'll get 3/2 u1 minus 3/2 u1 minus 3/2 u2. Okay, so d by dt u1 equals this. No real luck here. Not really seeing a pattern that'll help us solve it. Let's try the other variable. What happens? So this is as before. Now we have minus sign, minus 2v1 plus 2v2. Combining things together, we get a minus 7v1 plus a 4v2, which turns out to be minus 3/2 u1. This turns out to be something similar, minus 11 u2 divided by 2. So instead of having a equation that was 5 minus 5, 2, 2 minus 2, I have d by dt u1, u2 equals minus 3/2 minus 3 halves, minus 3 halves, and minus 11 halves. This is not really helpful. So simply taking a shot in the dark really is not going to help us be able to solve this question. So this is a total bust. So we're not happy. So at this point, we're basically, when you look at this, not only do we have nothing, we also don't know where to go from here. Like we see this, it's not like we would say, well, give me a little bit more of one thing or a little bit less of something else. So now, to show you that perhaps there are changes of coordinates that can be helpful, let's suppose that someone whispers in your ear. So we get a helpful whisper. So the helpful whisper we get is try the following. U2 equals V1 plus 2 V2. And let's try U1 equals, let's say, just V2. Let's give this a shot. So if we give this a shot, again, what do we know? We know that we can think of V1, so we know V2 is just U1. So V1 we can also solve. V1 equals U2 minus 2U1. So if we try this, let's see what happens. So let's try the second variable. That seems pretty simple. Let's try that one first, see what happens. D by dt of U1 equals D by dt of V2, which, as before, equals 2V1 minus 2V2. But now we can write this out. 2V1 is 2U2 minus 2U1 minus 2U1. So this turns into minus 6U1. So 2 times 2 is 4. Another 2 is 6. Minus 6U1 plus 2U2. So this doesn't help us really either. D by dt U1 definitely depends on U2. So let's try D by dt of U2. Now D by dt of U2, we can again go through the math. This is D by dt V1 plus D by dt 2 V2, which we can expand out. So this is going to be minus 5 V1 plus 2 V2, now plus 4 V1, so 2 times 2, and minus 4 V2, which, let's group some terms together. This is minus V1, 2 minus 4, minus 2 V2. Okay, we both have V1 and V2, but what is minus V1 minus 2 V2 in terms of U2 and U1? Well, now we're in luck. Something very nice has happened, and this is just equal to minus U2, only one variable. So now, if you look at this, what we have is we have U2, d by dt, U2, equals minus U2. This is a differential equation we know how to solve. So from here, we know that U2 of t equals U2 of 0 times e to the minus t. This is for every t greater than or equal to 0. So what is U2 of 0? U2 of 0 equals V1 of 0 plus 2 V2 of 0, which equals 3. So this thing is 3 e to the minus t. Again, this is for all t greater than or equal to 0. Okay, that's pretty good. We know how to solve this. But now we know what U2 is, which means we can do the same thing that you've done when you were doing Gaussian elimination, which is after you solve for one variable, you can back substitute it in. So we have another equation now. We use this. And now we know d by dt u1 equals minus 6 u1 plus 2 times u2, which is just 6 e to the minus t. This is for every t greater than or equal to 0, as before. Now, this is where we can use what we did last time, which was we understood how such differential equations behave when we give them exponential inputs in. Recall, that when you had a differential equation, d by dt, x equals lambda x plus u of t, where u of t equals e to the st for every t greater than or equal to 0, that we worked out what this thing's solution is. This thing's solution was get some constant e to the lambda t plus e to the st divided by s minus lambda, where this constant, of course, is going to be chosen to match the initial condition, whatever it is. So in general, you need k2 plus 1 over s minus lambda, in this particular case, to equal x naught. And you can solve. We've done this already. So we know how to solve this. This is going to have the solution u1 of t equals some constant, k2, e to the minus 6t. That comes from this part, basically, plus 6 e to the minus t divided by. Now, what is s? S is minus 1. What is lambda? Lambda is minus 6. So what is minus 1 minus 6? Well, that's minus 1 plus 6. So this becomes some constant, k2, e to the minus 6t, plus 6 over 5 e to the minus t. Okay, it's pretty good. What is that constant? The constant has to match the initial condition. So what is u1 of 0? u1 of 0 is v2 of 0, which is 1 volt. So we need this to equal 1 at 0. So this is clearly 6/5, which means k2, this must be 1/5. So u1 of t equals 1/5, or negative 1/5. Negative 1/5 times e to the minus 6t plus 6/5 e to the minus t. So remember, u1 of t, that's the same as v2. So now we know the waveform for v2. It has the sum of two different exponentials, e to the minus 6t and e to the minus t, with the following weighting. And, last thing that remains is we can solve for v1. What is v1 of t? v1 of t equals u2 of t minus 2 u1. So u2 of t, we know. This is equal to 3 e to the minus t from before, minus 2 times this, so minus becomes a plus 2/5 e to the minus 6t, minus 2 times 6/5 is minus 12/5 e to the minus t. Now, what is this? This is 15/5. 15/5 minus 12/5. This is going to be 2/5 e to the minus 6t plus 3/5 e to the minus t. And notice this agrees with the initial condition. At t equals 0, this is equal to 1. Again, this is for every t greater than equal to 0. So by someone whispering to us to try this change of coordinates, we were able to solve this differential system of differential equations. How did we solve it? We were able somehow to get out of this system of differential equations a scalar differential equation, namely this one, that we knew how to solve. Having solved this differential equation, we're able to back substitute and get another scalar differential equation, this time with an input that we knew how to solve, and proceed to solve it. So this is very powerful. So what we will talk about next time is how can we get these change of coordinates without having to have someone whisper them to us.